Okay, let's talk about Chapter 11, raster analysis. So, rasters are just a grid, if you will, a basic kind of grid, like the first ones you learned about in grammar school. And essentially what separates it from just a plain old grid is that this grid is referenced to a location on the Earth, and it starts with that XY location in that upper left-hand corner, pins that thing down, and then you can do all kinds of stuff with it once you know exactly where it's at. And so the thing about rasters is they're kind of unique in that you have a continuous surface of information. The format itself allows for a lot of interesting and useful techniques. And for a lot of things, it's faster than vector data simply because it's uh, processing and dealing with less things. It's just the one thing, and it's a repeated function over an area, so it works, pretty quickly. And then another reason that it's pretty useful and pretty important is because, well, got my yawn out of the way. Because a lot of remote sensing data comes in a raster format, and so it is the native format of a lot of the information that you use for a lot of the analysis. Two types, discrete and continuous. They're exactly what it sounds like. Discrete is something that we'd use to identify groups of things that have defined start and stopping points. Continuous is for a value or function that goes on theoretically forever, like elevation or temperature or what have you. Map algebra is really a pretty awesome technique we use. What map algebra does is it takes multiple rasters and it applies a mathematical function between the two different data sets to generate a third data set that is the product between the two. So for example, well, I could do it that way. I can also do it a slightly different way. In this example here, you've got raster data set 1 and 2. If you want to combine them together, the 5 and the 3 become the 8, the 2 and the 1 become a 3, the 7 and the 2 become a 9, the 4 and the 6 become a 10. Pretty straightforward. You can also use it to do conversions and other things. So maybe you've got a mathematic function where you take some value that's in your raster and you convert it to something else using an equation, and you can use the raster calculator in map algebra to simply take your raster data value and then apply some equation to it, and then that'll generate a new output that'll populate a new raster data set. You can also use rasters to do queries using logical expressions. Most common one is looking at an elevation and you want to select elevations in a certain range, and you simply just query it, and there you go. We can use a lot of Boolean operators with raster data as well. Ands and ors and nots and what have you. it it doesn't quite do the same thing, obviously, as what maybe the vector version would look like, but you can kind of see here how that would play out, because instead of looking at areas, it just looks at individual cells and do they meet the criteria. And so you'll get a little different output than what you might otherwise, but it's still the same basic premise. With and, it means it has to meet criteria 1 and criteria 2. And so if your criteria is, which cells are yellow, and you look at A and B up there on the right, the only one where it's and is the top right hand corner, and the or function is any of the right or bottom. The not or is the top, and the not's the bottom left. I mean, it's just as simple as that. Intersect and union gets a little more complicated. So the and is the equivalent to the vector intercept function. The or is the equivalent of the intersect of the union function. not is very similar to erase, and not or is can be achieved by using intersect and erase. This can get really complicated when you start looking at it. Raster overlays can be performed using vector or raster data. To do a raster version of the snail habitat analysis, you can do a Boolean raster for each of the conditions and then use the AND operator, and it ends up with only conditions that meet all of them. You can also, if you have all these data sets as raster, you can just use the raster calculator and multiply them all together. But that only works if everything's in raster. When you start working across different platforms, it becomes a little more tricky, but there are a lot of little steps and tools in there you can use to accomplish a lot of stuff. And as you're working through the tutorials with Price, good old Mary Beth will show you a thing or two. So let's talk about our friend, the raster calculator. Map algebra and Boolean overlays are performed using this tool. Here they show how you can do the snail habitat, and you have these condition rasters and elevation and limestone and dense trees, and it simply multiplies those all together, and you tell it what you're going to call it, put it in the folder where it's supposed to go, and then run the tool. When you do a Boolean overlay to determine suitable areas for like lodgepole pine, you have two raster data sets that you've created. One is the precipitation and one is the elevation, and then when you do the AND function or multiply one by the other, what are you going to get? Well, the only common space to both data sets is what you see there on the far end, and that is your habitat. You can also do an additive approach. This gives you more information, but it doesn't always give you the same information. So if you took the two data sets before, and instead of multiplying them together, if you added them together, anything that ends up with a value of 1 meets one of the criteria. Anything with a value of 2 meets two of the criteria, and anything with a value of 0 meets none of the criteria. That can get really complicated quickly, particularly when you have more complicated models. The bottom example is using the snail habitat model that had a lot more inputs, and when you use an additive model instead of a multiplicative, you end up with 1, 2, and 0, 1, 2, and 3 options. And so obviously the 3 is your habitat. 2 meets 2 of the criteria, 1 meets 1 of the criteria, 0 meets none of the criteria. What are some of the drawbacks? A lot of times conditions are gradual. There's just not as many clear-cut start and stop points in nature as what you might think. And so when we're looking at something like a habitat, it's not like there's going to be an imaginary line drawn where the lodgepole pines quit growing. It's going to be a high concentration of lodgepole pines to a decreasing concentration of lodgepole pines to a point to where you have an occasional lodgepole pine and then no lodgepole pines. So when you have a model that says 1500 meters is suitable, that's great, but what if it's 1501? Does that mean it's not going to work? No, it doesn't. So there's some techniques you can use to do this. Weighted overlay ranks conditions for a more realistic approach. 0 to 1000 is unsuitable, 1000 to 1500 is somewhat suitable, and above 1500 is ideal. And so this would give you multiple criteria. You could also create a fuzzy membership function as well. Again, we've talked about weighted overlays. K rasters represents K conditions. Each condition is ranked on a scale from 1 to whatever, how many criteria you have, best to worst. When you go through a process like this, what you're going to end up with is increasing numerical value is associated with a better selection. And it allows you to identify areas that are poorly suited, better suited, and ideally suited. So here's a nice landfill model. Weighted overlay can be used to do something like this. The lower the slope, the better, okay, because that means you have to flatten less stuff. Soil infiltration is important. You don't want a lot of leaking down into the groundwater, so you want low infiltration. You want closer to existing roads, that way you don't have to build a big road. And you want to be further away from streams, that way you don't have to worry about runoff getting into the streams. So you have 4 conditions, and so you can rank them on a scale of 1 to 3. And so when you get a value of 3, that's best, and 1 is the worst. So you divide up the slope into 3 classes, and greater than 20% gets a 1, 10 to 20 gets a 2, 0 to 10 gets a 3. And you can similarly see how the other data sets are broken up and assigned into the 1, 2s, and 3s. And then they're weighed based on what is most important. And so slope is not as important as the distance to roads. And the distance to roads is not as important as the distance to streams. And the infiltration is more important than that. So in this example, they used 0.1, 0.2, 0.3, and 0.4. And if you add those up, 3 and 2 is 5, and 4 is 9, and 1 is 10. And by 10 I mean 1, because these are fractions. And so this is basically saying 10%, 40%, 20%, 30%. So you would take the relative values there for each section, multiply it by the weights for those sections, and then add all those up. In theory, if you had a value of 3, and you multiply it by the 0.1, you get 0.3. You take the 4 and you multiply it by 3, you're going to get a value of oh gee whiz, 1.2. The 3 times 0.2 will give you 0.6, and the 1 times 3.3. When you add them all up, you're going to end up with a value of 3. I'm looking here at their model, and I'm wondering if they've got something wrong. Okay, so flatter slope gets a higher score. Okay. Lower infiltration gets a higher score. Less distance gets a higher score. Larger distance to a stream gets a higher score. Yeah, that's right. So if you take the 3 in each one, and you multiply it by the weight according to it, and you add it all up, you should end up with a value of 3. And so that's kind of what you're going to get with this. The closer the number is to 3, the better the location. Well, I could have saved myself a lot of thinking if I would just went on to this next slide earlier. The ranked rasters are added, and along with the once they've been multiplied by their weights, and it gives you this suitability indices, where a value of 3 is highly suitable and a value of 1 is less suitable. That still really only gives you like 3 categories of values, and so yeah, that does give you a lot more information than a simple Boolean model, but it doesn't give you near as much as what a good fuzzy membership function would. We can also do distance functions. Turns out that's a really useful thing in rasters, and that was something we used in that last model on the previous slide. It calculates distance from features is one way to do it. You can determine the direction of travel to the closest feature. You can use it to create buffers and determine things like the least cost path. There's all kinds of distance related stuff you can do, and they all have their own unique sort of utility. Euclidean distance, this calculates the distance from a set of vector features like streams. It gives you this new raster where every cell in the raster identifies how far am I from the other feature in the other data set. And that's pretty much just that. Euclidean direction calculates a directional raster. It shows the direction that you would have to travel to get to the nearest feature. The nearest closest feature. And so first it identifies where the closest feature is, and then it figures out what that direction is. And it gives you something like this. You can use a Euclidean distance to get and reclassify it to create buffers. So for example, if you calculate out the distance to a stream, you can then select everything that's under a certain value, and that would literally give you a buffer out to that distance. A straight line is, as we say out here in the sticks, as a crow flies, is the shortest distance between 2 points. But the shortest distance between 2 points is not always the easiest distance. So, for example, if a hiker is going to go from a spot on one side of a mountain to a spot on the other side, straight across is not always and rarely going to be the way to go, because you want to um, avoid impassable objects like rock cliffs. You want to select a path that's not super steep. You don't want to walk 100 miles out of your way, but you need to find that compromise of how I can get across here where I have the minimal amount of effort given my limitations here. And so an example like this, it can look at the cost of the slope, and it can determine the possible routes that'll get me to my final destination. And then looking at the slope as it changes across that, it can figure out what's the average slope of that path, and ultimately generate you a path that is less steep, and that's how this would work. We can also use rasters to calculate density functions. In this case, you have a bunch of information. For example, think of things like the COVID-19 cases. If you had them reported as individual point data from where people lived, and you calculate a density function, it would literally just give you an idea of how many people are infected, and it would do this in this distance basis where you'd have this function like this, and you can see whatever they're looking at here. There's a lot of it in New York, there's some in Chicago, and some in Los Angeles, and some in Texas and Florida, and then it's more scattered out everywhere else. Two types of density functions: a simple function, which assumes that the weight values occur exactly at the feature location. Um, and so counting impact craters on a planet's surfaces is kind of an example of how you could do that. A kernel density function spreads the values out over an area using a Gaussian distribution before the counting. This is better for population which is not concentrated at a single point. And so like you have a city, and you have a point data for the city, and you have a population for the city. All those people don't live at that point, they live out over an area. What a kernel density function does is it spreads that value out over according to a Gaussian distribution, and it does that for each of the known points, and then calculates density from that distributed function. So it's a lot more complicated. Interpolation is one of the great tools in GIS. Interpolation estimates values between known points of measure. In other words, it takes the data you collect and fills in all the spaces in between. There's lots of techniques. Some rely on mathematics, some rely on statistics, some rely on first law of geography, and some are just based off of things like regression. We're going to talk first here about inverse distance weighted. This is the most common technique. This kind of relies on this concept of the first law of geography by Waldo Tobler, which states that things that are close together are more alike than things that are further apart. In other words, there is spatial autocorrelation, in that things don't change, generally speaking, dramatically quickly, and that in the broader, larger sense of things, stuff that's near one another tends to be more like one another than stuff that's really far apart. And so when we use something like nearest neighbor, what we're doing is we're saying we know this value is this at this location. We assume that places near it is going to be similar. And so with inverse distance weighted, for any location that you spot on a map, it finds the closest value, known value, and that value will be weighed most heavily in calculating the new value at the unknown location. But you can tell it to go out to a search radius or select a certain number of known points, or however it is to do that. And ultimately, as you move around, those values will shift. They tend to focus and center around the known points, and so sometimes you'll hear people refer to this as bullseye mapping, because you kind of get these nice little intrinsic circles around your known points when you do nearest neighbor interpolation, or not, no, I'm sorry, not nearest neighbor, inverse distance weighted. Surface analysis. There's lots of raster functions that do and use this that are really important. Slope is a big one. So is aspect and hill shade. Here in A, we have this nice little digital elevation model. And from a digital elevation model, you can calculate slope, which is the change in elevation over a linear distance. You can calculate aspect. Aspect is the direction of the steepest slope. And you can create hill shades and view sheds. Hill shades simply take and create a fixed position for the sun in the sky, and then based on the configuration of the landform, it shadows the side of the DEM that is away from the sun to give it a more realistic approach. Now, oddly enough, it has a default setting for where the sun should be in the sky. You can change that. Clearly, if you're in the southern hemisphere, it's not going to look the same as what it does in the northern hemisphere. And from one season to another, that angle and position changes as well, as it does during the day from early in the morning to late in the evening as it tracks across the sky. This gives you the shades and shadows at one point in time. You can change that if you like. And then view sheds. View sheds are simply a linear sort of math function that says, okay, if I'm standing here on this DEM, what can I see from here? And so things that are blocked out because of other features being in the way, or things that are down in a valley that you can't see because when you try to angle down to the bottom of the valley, you'll be hitting the hillside or the shoulder slope or something like that. It blocks it out, and ultimately what you get is a polygon that identifies, and this is the places you can see. So let's look about slope. Slope calculates the steepness of a DEM. You have two options, degrees or percent. If you're in degrees, it's just the tangent of rise over run. If you want to calculate in percent, it's percent slope. It's just rise over run times 100. Not super complicated. Aspect, the only thing about aspect that can be a little confusing, aspect comes out as a value between 0 and 360. What you have to remember is that due north is also 0 and 360. And so when you look at a direction like north, north is not always a single number. A lot of times it gets classified out to be, just to the left of 0 and just to the right of 0. So it may go, for example, from about 340 to about 20 degrees. That would be north. Typically when we look at north, south, east, and west, we also throw in there like northeast and southeast and southwest and northwest. And what we're doing when we do those is we're creating subdivisions, and once you create these subdivisions, ultimately you have to draw a line in the sand somewhere where it stops being north and starts becoming northeast, where it stops becoming northeast and becomes east, where it stops becoming east and becomes southeast. And so there'll be a range of values that would represent these. Or you can simply represent it mathematically as its direction, which could be anywhere from 0 to 360. Hillshade, it's the gray, and you can sort of see the darker grays where the shadows would be. Viewshed, you got a location point. What can I see from there? And it does that. You can put in the height. You can talk about trees or whatever else you might need. There's all kinds of ways you can set these tools up to run. You can also set up multiple observer points. And you might say, well, why would you do that? Well, what if you're trying to figure out where to put fire towers, a network of fire towers, to be able to see the most space? And you've got 10 different locations you can build, but you can only build 2 fire towers. You can look at the different combinations to see which one has you the vision of the most area. Neighborhood statistics. They function on a neighborhood or a window around an individual target cell. They're usually square, but you can also have other shapes like circles and wedges and annuluses. Um, and then it calculates statistics for the neighborhood, like what's the mean value or whatever. And then once it has that value, it moves to the next target cell for evaluation until the entire raster is produced. This is a focal function we're looking at here, and basically the window moves one cell at a time, and so there's overlap. If this was a block function, it wouldn't overlap. It would, you know, calculate it for the whole area and then move on to the next one. Um, uh, I like it when I get ahead of myself. Uh, Block neighborhood function is like the top. Once you use a cell, you don't use it again, you move to the next one. A focal neighborhood function moves one cell at a time, and so you have all this overlap. What is the effect of that on data? Here we have a land cover map A, and we use a majority filter. So what is a majority filter? Majority filter looks at what the field or the thing that you're interested in is, and whichever one's the most common value, that becomes the value it uses. So if you have a 4x4 cell, it's going to look in those 16 cells and say what's the most common value. That's the one you get. So if you do this on a focal function of B, you see how it kind of smooths things out because it basically just dissolves away little tiny pieces of stuff and moves on from that. If you do a block function, it does it even more so, but the big difference is it becomes more coarse. Because in the block function, that 4x4 becomes everything in that 4x4 has to have the same value. And so while it might still have the same resolution as the others, it's effectively acting like it's a much more coarse raster, and so you get a much different looking output. How do we simplify rasters? Rasters can be converted to features. Complex rasters are problematic because it generates all kinds of tiny little polygons. Um, and so what they've done here is this land cover raster has been subjected to 2 passes of a focal majority tool on a 4x4 window. So you do that 4x4 window using the focal function to identify the majority. You run it once and you get a new output. You run it again on that same output. Each time what happens is you're going to reduce the number of smaller things and blend them into the bigger picture. And then when the tool decides to make things into polygons with much less variability and with more heterogeneous sections, more homogeneous sections, and less heterogeneity, alright, can't talk today, with bigger chunks of stuff that's the same and fewer little chunks of different stuff, you have less polygons, and the polygons tend to be bigger and more connected with less little incursions and inclusions in them. So that's what this would do. That's how simplification would work. Zonal functions are really awesome. They are also a type of neighborhood statistics, but the neighborhood is not determined based on a simple thing like a focal or a block function. It's based on an entire another data set. You have a second data set that you say, these things here, this is my zones. Typically, we're talking about a bunch of polygons, and each polygon is a zone, and what it will do is, for that particular zone, it will then calculate some statistic from the raster cells that are located within that zone. That's all it does. This is useful, very useful. So let's look at some examples here. We have zonal statistics, looking at watersheds. Then we have a slope raster, and we calculate out the average slope in a watershed. And somebody might say, well, how would you want to know the average slope in a watershed? What possible use could that be? Well, believe it or not, discharge from a watershed, in other words, how quickly water leaves a watershed following a significant rain event, is directly proportional to a lot of factors. One of those factors is the steepness of the slope. The steeper the slope, the faster the overland flow. So, if you have a watershed that in general has a higher average slope, that means that when there's rain, that water will be discharged much quicker than what a less steep sloped watershed will. Reclassify is another tool we use a lot. It basically takes values in the raster and converts them to a different value. It creates a new field. You can then take that field, look it up, and create a whole new raster of just that data. Lots of interesting and cool things you can do with Reclassify. Lots of different and interesting ways to use it. Spatial Analyst is an extension that does all kinds of stuff. In the Spatial Analyst tools, there's tons of raster related things. This extends the standard tools in the geoprocessing pane and has a lot of other functions, and they're organized into toolboxes, and you have access to all of them. But when you get outside of the educational environment and you go to work somewhere, you may or may not have all of these tools. Environments are a clever little way of saving some work. So you can go into your environment settings and look at things like your processing extent and your cell sizes, and you can apply masks. All these help you define areas that you're working in, what stuff you're going to consider, how far you're going to consider, and sort of automatically trim down your study areas. And it doesn't really do anything that you can't do by another means, but if you have multiple and complex repeated tasks, you can utilize your environment settings to eliminate some of the steps by doing things like making new outputs all in the same final coordinate system that you're looking for, so you don't have to do a bunch of projections. You can use things like masks and processing extents to control what data gets analyzed and what doesn't, to make the processing extent smaller, so that there's less data to work with, and you can basically clip it down to the area of your mask or the area that you want to do the calculations on. It can save a lot of time, and it can also save you a lot of steps. So some of the workplace settings that they want to talk about here is where your current and your scratch places are. Some people call it the junk database and the working database. I don't care what you call them. Output coordinate systems are important. I like to take care of all my coordinate issues as early as possible, and so that this doesn't become an issue, I'll set the coordinates up in a map or a document, and then as I bring in data, I'll automatically go through and systematically change it into the format that I need, and then remove the earlier copies of the data so that I only have in the final data sets that are in the right coordinate system to work with. Processing extents. This can help. Sometimes your rasters don't line up, and sometimes you have different cell sizes. If you don't specify how you want a lot of this stuff done, it's just going to do it, and so it'll resample it, and you may not even know what's going on. It's best to think about this stuff and work through it ahead of time. Cell size, there's some funky Esri math they do to calculate a cell size for a lot of tools that typically ends up giving you very tiny cell sizes, and that means that your data sets are just unawesomely huge. And so if you know what cell size you're working with your raster, my advice is you can only be as accurate as your least accurate piece of information. And so if you've got a 30 meter DEM and a whole bunch of 3 meter satellite data, ultimately you're going to need to want to work on the 3 meter scale or the 30 meter scale. And so you would probably want to go ahead and do that resampling of the 3 meter, whatever the stuff is, into the 30. Now you can look at that two approaches. You can do your analysis on the 3 meter imagery or whatever it is until the end, and then take that last final product and then make the conversion. That would be my recommendation, but you could make an argument that the other way might be better because the complex analysis would be done on smaller data sets. Masks are basically just a way to clip rasters. So you pick a mask and you assign it. When you do analysis, it'll cut it off at the borders of that. Resampling is the process that we use to match things that don't match. A lot of different techniques.